Well, hi, welcome to my shop and thanks for joining me here. It's December 23rd, just a couple days before Christmas. And a couple of my viewers, perhaps you, have asked me, hey, what are you doing for a Christmas special? And I thought about it and thought, what do I want to work on over Christmas? And I've decided this is the guy. Now, I've done one video on this. Chances are you've watched that video and you're watching the next one, which is this one, which I'm just shooting now. Lots have happened. Lots has happened between then and now. So last time I looked at this radio, I really had no clue about it. Since then, I've learned a lot, and thank you to viewer Mark. Mark, is that you right now? Are you watching this right now, Mark? Thanks a lot, because with your help, I'm able to go forward. Without your help, I wouldn't. And what did Mark tell me? He told me what radio this is. And after a little bit of research, this is really an important radio in radio history. I'm really quite pleased to have this on my bench. You can see right on it, it says Ultradyne Super Het Set. And from my research, and maybe I haven't done enough yet, this really represents the first super heterodyne radio produced in a kit form for sale, for commercial use. This radio has some circuitry in it, I could say. I mean, along with just the whole super heterodyne technique. It also has a very unusual oscillator in it, which is, I think it's non-intuitive. I think you can look at it and not really grasp how it comes to oscillate, I think. So lots of interesting things in here in this radio. The guy who invented this radio, I guess the whole radio would be his design. There's a French guy named Lacault. Lacault, I'm probably pronouncing it quite wrong. It's L-A-C-A-U-L-T. Lacault, something like that. And so his claim to fame is the invention of this peculiar oscillator circuit and the use of it to generate a super heterodyne radio. All radios today are super heterodyne radios, pretty much. So 1925, I believe, is the date for this one. Now, it would have come out as a kit of parts with instructions, and the kit builder would have fetched himself not a couple pieces of plexiglass, that's for sure. He would have grabbed a couple of boards and would have drilled them and fixed them all up so that you could put all these parts on it and lay it out, do all this careful wire bending. Look, no insulated wires in here at all. Gives you an idea of the vintage of it. Yeah, buying a wire with insulation on it, hey, that's money. So that's one really interesting thing. I know what the radio is, I know its place in history, and it's significant. If you look at the front of the radio, I mean, you can see there's an oscillator control. Today, in a modern radio, we call this the tuning knob. But really, it's true. It's an oscillator control. It's really what it is. And then here's control. It says mixer on it. Not quite sure yet what this is all about. What can you possibly be doing? It's driving a capacitor behind there. It has to be a tuned circuit of some sort. So it must be a tuned circuit in the area of the mixer. I'm not quite so sure. We looked at this in the last video, the grid leak control here, and concluded that this must be some fancy kind of variable resistor happening in here. Not quite sure about that. Goodness knows if this is doing what it was supposed to do too today after all these years. So another thing of interest was all the tubes that are in here, including these two large rectifier tubes. Turns out, and these are all 26s, as best I can tell from what has been penned onto them or written onto the tubes. So I have 1, 2, 3, 4, 5 26s and 2 probably 80s. These are probably number 80s. All wrong. Totally wrong tubes. When I looked at this last time, I was saying to myself, and I may have spoken out loud, the vintage of this radio is at a time when there was really only one tube out there, the O1A. There's a couple other tubes, but the O1A was the king, triode. Now, this radio should have 8 O1A tubes in it, not what it's got. So how does it end up with these tubes? Well, if somebody has this radio, they don't know anything about fixing it, they're not about to fix it. It sure looks ugly without tubes. So if you have a bunch of old tubes, you can jam the tubes in the socket, and now it looks a lot nicer, doesn't it? And that's probably how they got in there. Somebody probably just plugged them in, no intention of ever operating this guy. So, good thing. Thank you again, Mark, for clarifying all this. Now there's another piece I know about this radio at this point, and that is the condition of all these transformers here. I ended the last video realizing that one of the very next steps would be to prove out these transformers. I also know radios of this vintage typically have defective audio transformers, and often you can tell that these have been changed and upgraded because the earlier ones have failed. Sure enough, these two guys appear to have open circuited primaries, both of them, from the test I did. So on the audio side, that's not very good news. These transformers are not 1-to-1. They're called amplifying transformers. They have a ratio of maybe 1-to-5 or something like that. I'm not exactly sure. So they provide a bit of a boost between the tube amplifiers here. So for now, we can just kind of ignore this part, and maybe this tube too. Just ignore this. The radio will still operate. I'm pretty sure this one should be included. Will produce an audio signal. I can grab that audio signal and send it off to some other amplifier. We don't have to worry about these. So in terms of the operability of the radio, even though it's got defective transformers here, it's still really good. Now what about all these? So these are interstage transformers coupling the signal as it's being amplified through the tubes. Yeah, I think it's going this way, down to this end. So each one of these has a trimmer capacitor. Each one looks exactly identical. It all looks identical. This looks smashed down. Let me pull it up here. Put it in the same position as the others. So I took my ohm meter out and I checked all these. There's a distinct pattern to all of them. I can't remember the exact values, but the primaries measured the same all the way through, and the secondaries measured a different amount but the same all the way through, and not this one. This one, the secondary measured half the resistance of the rest of them. They all look identical. So my conclusion is something's going wrong at this one. Could be my test wasn't quite valid because of other stuff hooked up here. But the good news is the rest of them seem fine. At least they all seem the same, and they all have a reasonable amount of resistance in them. Another thing we found the first time through was there was no resistor here, and this is the detector stage. This is a grid leak detector. So I grabbed one resistor here, grid leak resistor, which I showed, and I put it in, not knowing if this is the right amount or anything like that. It was a typical thing back in the day when these radios were operated to have 2 or 3 different resistors here, and to change them in hopes of improving the reception as you were working on the radio, working with the radio. Okay, so to get anywhere further with this, I think I need 6 O1A tubes. All these guys come out, and that's not even easy. You notice these are all on rubber mounts because these tubes were very microphonic, and so any tapping is going to come right through them. You know, the O1A, I guess, you know, I'm not super expert on these tubes, but these tube sockets are really grabbing the tubes here, and I don't want to pull it out against the spring here. You know what I mean? I want to. There. National Union. This is a 71A. That's a valuable tube. 71As are valuable. It's not even a 26. Has nothing written on it. Yeah, so this is like just a random tubing. Ooh, that didn't sound good. Sounded like the glass globe was coming off the base. Nope, still hard. So this looks like an 80. No, it's a 5Z3. 5Z3. I guess maybe I read that last time. Definitely a rectifier tube. It would have been a real disaster if I tried to fire this radio up with these tubes in place. It would not have gone well. So once again, Mark, thank you so much, Mark, for getting me on track here. So this one has somebody's pinned in 26. And you might be able to read that with a magnifier. I'm not too worried about these tubes right now. It's the 01As. Now I have some. Stunning to me, I have 10 01A tubes. That's a 26 for sure. Made in Canada. Westinghouse. It's got a date here from 1922 to 1939. So for them to stamp that date on there, it had to be post 39. That would mean this tube was, of course, this tube has nothing to do with this radio. So stop right there. Stop right there. Must have been quite an undertaking to put something like this together back in 1923. Can you imagine how exciting it was? Get this together and then start trying it. There'd be maybe, I don't know, 1923 there might have been 10, 20 stations in the United States. Maybe one in Canada. I'm not even sure if there were any in Canada. Get this thing going, and then just like you heard at your neighbor's place, you'd hear voices coming out of it. Wouldn't that be exciting? That would just be thrilling. So again, this is handwritten 26. He's written it right on the label spot. So made for Canadian Electric Company, but who made it? They're keeping that secret. Okay. Well, there's a big whack of tubes out. Oh, one more. One more to get out of here. Oh, that came out pretty easy. Oh yeah, I looked at this one before. Oh, this is the one with the, look at the pins on it. This is the worst tube I've ever seen in terms of pin corrosion and the like. It's terrible. 80. It says 80 right on it. I can read it. 80. Valuable tube if it's in working shape. Now we got something here. What do we got here? We've got a chance now. I should ohm out all this stuff again right now, and just to double check everything. And another coil here I should try ohming out, but I really don't know the connections. And then if you look at these wires running along here, they all go under these screw type connectors. Boy, that's tight. So if these have been left totally undisturbed from the day they were clamped down in 1925, oh no, it would have been undone and redone when they mounted it back onto this plexiglass. So whenever that occurred, I wonder when plexiglass came out. It might be an older material than I realize. So yeah, let's just go ahead and ohm those guys out again. It's a good thing to double check all this stuff. Making decisions about how to go forward. That's not going to work there. There it is. Based on these early indications, and more than once I've been quite wrong on the early indications. Like almost all the time. Okay, so we're on the 2000 ohm scale. Here's my meter working. So primary, secondary. Primary side here with the wires attached. I put this to a higher resistance, 20,000 ohms. You know, I gotta go way high to be sure. 2 million ohms. I really want to be sure I'm getting. I found that these wires are very hard to make a connection with. See what I mean? So they've really got to There's a little bit there. Really filthy wire. So you can imagine all these screwed down connections are bad. So nothing there. Okay, on the secondary side, we're going to take this down to 20,000 ohm scale. 6,000 ohms on the secondary side, which apparently is about right. I'm going to try this one, primary side. Let's go back up here just to be sure. 2 million ohms there. Primary side should have a lower resistance than the secondary side. Secondary at 8,000. So one at 6,000, one at 8,000. So secondary wise, these are good. Primary wise, they appear to be open. Is that a surprise? No, not a surprise at all. Now, let's go through these ones. So it's got to be primary, secondary. Why does it have to be that way, Jim? Because the signal's going this way. Because these are hooked up to this tube and these are hooked up to that tube. So for sure it's going to be. So we'll do the primaries first. (2,000 ohm scale). 130 ohms. Well, you see that? 140 ohms. 150, 130, 130. So they're all matched. So I mean, that's really reassuring. Now we'll do the primary side. $85 ohms. 90 ohms. 85 ohms. And now, the weird one. 40 ohms. Exactly half. Could be on purpose. This is at the head of the line. Maybe things are different up here from down there. Maybe this capacitor's leaking. Yes, that's a capacitor. We should look for shorts between the windings, so we'll go along like this. Oh, don't think we were supposed to see that, but maybe that's okay. Let's see how it compares. So shorted right there. Did that just change things here? It did. Huh, that was a short. Doing that. Okay, so we hope to see open circuit here. I should put this on a higher resistance actually. 2 million and we'll do it again. Resistance between windings. Hey, the radio's laughing. It's just, it must be tickling it or something. Has a funny giggle. We're golden. Except for the funny resistance here. That's beautiful. So these transformers are the IF transformers in this radio. That's obviously the trimmer for them. And from what I read, the intermediate frequency is around 100 kilohertz. So it's actually below the received frequency. 100 kilohertz. That would mean the local oscillator would have to also be below the tuned frequency. That might make some sense, and because the higher the frequency, the harder it was to make these things work. So it tended to stay low with frequencies back at this time. Next stage, let's see, what would it be? So, you know, visually this looks intact, although it looks a little roughed up, it looks intact. These kinds of controls could have all kinds of trouble with contact. Down here, contact problems. We get to that later. Not too much can go wrong with these guys. This could easily be defunct. This must be the antenna coil way out here, and this must be the oscillator coil, although I don't really know for sure. I mean, it has to be an oscillator coil, I'm pretty sure. So it must be this guy. There's a capacitor right here. There's 1, 2, 3, 4 capacitors. This one won't be used, so it becomes handy, maybe for being relocated for some reason, should that be necessary. Why wouldn't I plug in 6 tubes and turn it on and see what happens? Risking the tubes a little bit. Tubes themselves, I have to test. I've got 10 tubes. For all I know, I got 10 bad tubes. And these are really, really old, very early tubes. So just in reading up on this stuff over the past year, I should be a little bit careful about operating such old tubes initially, because there's a good chance that there's gas ions floating around inside the tube, and when you operate the tube, if you apply voltage to the plate and the cathode, the ions will head for those two structures right away and potentially contaminate them. And where you really want these ions to go is into the getter. Let's just grab one of these tubes here. So these aren't quite old enough, but so all this shininess in here, this mirror light, this is all getter. So the recommendation is you take one of these tubes, really, really old tube, and you don't apply the high voltage to it. You just heat up the heater and leave it running, because apparently the getter won't, the job of the getter is to collect the free ions that are floating around in there, and I guess they just fuse to the inside surface of the getter. This isn't very active at low temperatures, so when the tube needs to be hot for the getter to work. So all in all, if you want to if you assume there's gas in the tube and you don't want to hit the high voltage and ruin the tube, or not really ruin it, but just take it down a notch by accident because you've flown all these ions onto these surfaces, you need to heat it up and let it sit for some length of time. You know what would be possible would be to take one of these tubes, do it with this one, test it for gas in a tester that I've got that will do a gas test. Most of them will. It has to do with grid current, detecting grid current and analyzing grid current. Check it for gas, then leave it. Assuming there is some gas in it. Leave it on, hot, and then test it again later and see if the amount of gas has dropped. Now, that's all on the assumption that there's gas in here. So I just don't want to be the guy who's accidentally taking these tubes, which potentially have more life in them, and wasting it because I don't realize, what's going on in them. They look empty. They look empty, for crying out loud. Just like space. Hey, when I was a kid, empty space, empty space. They don't say that anymore about space. Apparently, space is full of junk. That empty space, full of bits and pieces of the universe flying around. I'm going to get out those tubes. We're going to take a look at them. I'm going to test them and see if I can find at least six good tubes. And I heard my cat. Did you hear my cat? I heard my cat. I'm really quite surprised I have so many O1A tubes. There they are. And in here it's not just O1A, but also some Rogers tubes are very common here in Canada. These coated kind of tubes here. So here's the O1A. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Maybe that's not. Some of these, ooh. Doesn't sound very good, does it? Well, so I was giving a little speech there about these old tubes and the initial turning of them on after years and years and years and having a small amount of ionized gas inside. It's going to cause trouble and remove a bit of the remaining life of these tubes, if there is any remaining life in them. So the idea is you should heat them up for some number of hours, in fact, and then slowly the gas will be absorbed onto the getter inside the tube, and then you're better off. I did talk about doing an experiment here. Could still do that and just not use an O1A on the experiment. And just do it. Yeah, I got all these other tubes. I could do lots of experimenting here. So I'm also thinking, if I'm going to heat these guys up for a couple hours, do them one at a time. That's like a day of. Why would I do that? I have this whole rack of tube sockets here. I could put a whole rack of O1As in here and heat them all up at once by using the radio, which seems to me to make a lot of sense. So that's what I'm going to do. I'm going to fill this guy full of O1As and probably face a lot of problems with contacts to the heaters, but that's okay. That's part of getting this radio going. Okay, so I don't have to do this. I'm working away on it when I realized, oh, I must have a record of all this stuff. Good, so I'll be able to pull out 6 good tubes. Now we got to figure out what we're going to do with them. 6 tubes. 6 tubes, 8 sockets. Which sockets do we leave empty? Up here. Well, I would say it's got to be the audio sockets. 1, 2, 3, 4, 5, 6. This is the oscillator tube, and it works in conjunction with another tube using a technique I don't understand. This is what made this guy Lacault made him famous for back in his day. Famous among other radio experimenters. I think that's probably the closest, best way to describe it. So if we look at the heater lines are here. These 2 wires are the heater lines. This upper one must be a ground because it's working its way into various things. The lower wire feeds. So are these? So these are both the heaters, are they? How's these sockets? Because the pins don't actually line up with that. They don't quite line up. Just to make it a little more tricky. Okay. Let's find out how this works. So I'm still inclined to do the heat them up and leave them for a while thing. So this would be one heater terminal here. Well, these are the larger holes, so it's got to be this one. This heater. Now the heaters aren't just heaters in these tubes, they also perform the function of the cathode. So if I stick one of these tubes in, number 7. Wait a minute, just before I put it in. No tubes in, you would think the heater lines would be open circuit. So I look here. $45, $85. Hey, where's the heater? Where? C minus, B minus, 135. 85, 45, VA. It's not jumping out at me here. So somewhere there's got to be a connection between these two wires back into here. Well, most of the wires coming out of this panel are heading down this way. These ones. Huh. Yeah, I'm not so sure I'm going to be able to sort this out by looking at it. You can practically see into the socket. You can practically see the metal connection coming out there. Okay, a larger pinhole. I mean, it has to be that the terminal closest to the hole is the one. I mean, it has to be that way. But this one is arranged where the holes are lined up with the screws. This one is arranged so that every hole is between two. So these are definitely the heaters here. Let's try this again. Well, I should. Well, if these are the heaters, I can see these coming to these two lines. For sure, I'm right about that. $50. Where's 50 come from? There we are. Just convincing myself that okay, I've got that one down to 0. How come this one too? So right on these it says G, P, plus and negative. So the plus and negative are the heater. Is the heater, I'm pretty sure. The heater is the cathode. Plate, grid, and plus and minus. Plus and minus. So these are all connected together. So if I go like that, we should see. That's kind of interesting. Kind of proves out the connections here a little bit. And then the other one would be here and here. Yeah. So now resistance just between the two. Is there any shorts in the radio is what I'm really after. Any shorts or anything? Ooh, something there. 50. That's what. So where's this 50 come from? Something to do with this? Something to do with this guy? Something to do with this guy. Combination is 50. No, it's 70. How do you get 50? 50 ohms. There's no resistors in this. There's really no resistors in this set. Except for these. Huh, isn't that something, eh? when I look at those European radios, there's like 1,000 resistors in them. They sound a little better though, don't they, than this thing? Will sound. This doesn't look right. Looks like it probably should have been bent a little differently in here. Oh, just as loose as can be, eh? Boy, boy. Well, there could be short circuits in here that are affecting these measurements I'm doing. That could be the case. So what I'm trying to prove now is that I can apply, what is it, 1.5 or 2 volts, 2.5, whatever it is, the right voltage to power up these tubes on the heater rail. So if I should go ahead with no tubes and energize it, that should tell me too. I'm still trying to figure out where the terminals are here. Could it be 45? 85? Is there something wrong with how we labeled these? Is the heater done in a totally different way here that I haven't spotted yet? Heaters. I should start separating these wires a bit here at this point, because that came right off. Yeah, the knurled nut is missing. That's okay. It's one of these audio transformers, so it doesn't really matter. Shorts all through here. Yeah, there's a reason why insulated wires are better. Of course, these guys have such a patina on them, they're practically insulated now on their own. Broken solder right here. You wouldn't even see it unless I did that with it. Is there something I could damage if I put, like if I hook up power to this without really knowing what I'm doing? Is there, look at this, a short right here. Looks like this should probably go under also, and it got over. Got the over-under wrong. Well, you can't exactly bend these things, stick them under, and then straighten them out again. That's a disaster. Yeah, this just doesn't look right at all. So I could temporarily insulate some of this stuff. Put split sleeves on it. I'm going to do something here. Just tighten this guy up and it'll hold it in the air. No, there's a lot of force coming down. So I would throw a little black tape on there if I could find my black tape. Can't right now. So what we'll do is, oh, for crying out loud. Stop for a minute. That's what we're going to do. Okay, so I'm just putting a little masking tape on here. Any more of these kinds of things around? This is pretty low here. Maybe this is the problem. It should be up like that. Yeah, probably straight across is how this should be. Okay, no contacts. Okay, so I'm going to use a power supply here. Let me just get a couple of good, just get a cord. Now these tubes draw a fair bit of current, so my little power supply may not be able to do it when I put tubes in, but at least I can check the sort of the continuity. So we'll just pick, oh yeah, getting on these I don't know, I'm going to make contact here. Okay, no tubes in, no current should flow. at all. So we're watching a meter you can't really see. This guy here. Switched on to milliamps, the meter. Turn up the voltage. This is already up a touch. And you can see current flowing. So there's more to this than what I'm doing. There's got to be more to it. If it was just a bunch of heaters, should be able to put voltage on it and nothing happened. No current flow. But there must be coils or something involved somehow. You know what? Maybe from here the schematic is a good place to go. All I'm trying to do is figure out a way to heat up 8 tubes for a few hours at this point. Well, let's look at the schematic. Okay, so here is the schematic page. There's a couple different radios on it. Mine is this one down here, the L2 Ultradyne improved. Well, I don't know. Is this the unimproved one up here? This only has one audio transformer. This one has 2. This one has 2. Well, I think it's this one. These two look pretty similar. Something going on here with this. Okay, so using the word modulator, I read somewhere about that. It's not a word. It's not the word we would choose today. But I think this has to do with the oscillator. Here's the oscillator circuit down here. This doesn't look that unusual, does it? B plus. Doesn't look that unusual to me. Looks like an oscillator here. What I read up on suggested that this worked in conjunction with another tube, and the plate was not served with B plus. So this looks different. So I won't dwell on that just now. My eye just caught this. What is all this supposed to mean? Well, maybe this is the that rubber tire resistor arrangement. This is where you drop in the I don't know what they're showing. This is where you drop in the resistor. It's in the right position. It's just before the audio. So this would be audio. Yeah, so this must be the detector right here. Oh, here's the detector. It's always on the grid circuit. So here's the actual detector. This must be where, oh look, there's a jack here and a jack here. This looks like a jack. So maybe you could plug something in here and sneak out. Maybe you sneak in. You sneak, this is probably phono in. Phono in, and then you have the audio amplifier. And you're pumping it in right where the detector's producing audio. That's what that has to be. What are these? R1s. Not present in this radio. That's interesting. I don't know what these are. R1. Didn't see anything like that in the radio. Don't know what those are. So what I'm thinking is I can supply I can take each one of these transformers and test them separately. I can supply a signal into the front. You know what I can do? You know what I can do? I can use a sweep generator, sweep these guys one at a time and see what they do. That sounds like fun. Okay, I think I have things set up here. I'm just going to remove a couple of unnecessary things here. Make it a little simpler to look at. So I have an input and an output coming to this transformer. The input is coming from the sweep generator. Sweep generator is set something like 50 kilohertz to 200 kilohertz, somewhere in that range. And that's being reflected up here on the scope, which you'll see better in a moment. The scope connection is made here on the output side of this transformer. So input side, sweep generator, output side, scope. The scope sweep, let me just change the lights here a little bit. I can see that quite clearly now, actually. So the scope sweep is being controlled by this guy. This guy is sending the sweep over. It's not the scope sweeping itself. So the sweep is coordinated with the frequency that's ramping up over here. So this is the bottom frequency, the top frequency. So if it was 100, I think it would show up somewhere in this area here. Sorry, 50 here, 200 there. That would be, yeah, somewhere maybe in this area. So all I got to do is just crank up the signal level going in. So let's take a closer look at the scope. And I'm going to do that. I'm going to crank it up here. And there's a response. Right there. You can probably see that on the other camera too. Yeah, I think I'll just stick with this shot. I can make it a little bit bigger. There we are. Now you can see it really clearly. Now what I want to do is fool with the trimmer down here and see what kind of trimmer range, and give me some idea of what the real resonant frequency of these transformers are supposed to be. Okay, stick it in there. Okay. Now watching the scope very carefully. Okay, it's moving to the left. The other way. It's moving to the right. Not moving very much. Wow. Okay, so I'm going to tighten it down. Oh my gosh, it's way over there. You know, I'm going to change the sweep on here. I'm going to reduce it. Reduce it this way. This way. I've got to lower the sweep start also. Oop, a little too quick there. Okay, now let's just check here. I do have a frequency counter going. We'll stop the sweep. The sweep is starting at 90, so 90 is where the dot is right now. And it's ending where the dot is at, what happened there? 0? It's okay, so let's, we want it up, let's put it around 100, because it seemed to me it was below 100. Let's see what happens here. 110. So it's going to go from 90 to 110. Well, that's not very much, but away we go. Okay, I don't see anything on there. So we will raise this number. We will lower this one. There it is. Okay, let's stick in the middle of the screen and do this a different way then. It's about the middle where I would like it. Let me stop it. So the sweep is starting at 6 kilohertz. 6 kilohertz, right? 6 kilohertz. And it's stopping at 114. And roughly in the middle here, that's like 75. That's not at all what I read. Okay, but we can now take this setup and just move it transformer to transformer, and see how each one of them stacks up. Let me tune this one again, just to see what... Ooh, get your hand away there. So we can move it all the way to there, and all the way back to there. Not very far at all. We don't know what exact frequency that is. Okay, now if I just grab a little more light here. So I can kind of see what I'm up to. What we'll do is we'll move now to the next transformer. Okay, look up at the scope again. Oh, that didn't work out, did it? A little bump there. The last one had a bigger bump. Did I do something here that's made it bumpless? It's about the... Oh! I think that's a losing the ground connection there. That'd be it. Oh, so what? It's very weak in comparison? Seems to be a bit of a second thing happening right here. Let me turn up the signal strength here. Yeah, look at that. There's some weird extension out here. Let me turn the trimmer. Let's see what happens. I had my phone in my pocket all that time, so I apologize if there's been phone chatter on the video. There we go. Oops. Didn't seem to do much of anything. Some kind of resonance in there anyway. Let's go to the next one. I don't want to think too much, just make observations here. Start putting the puzzle pieces together too soon and end up with the wrong picture. Oh yeah, this is the one that the solder is fractured on. Are we on there? Oh my gosh, look at the result there. That's dramatically different from the last one. I can turn this down now. Wow, okay, so there's something funny going on with the last one. Let me turn the adjustment here, whoops, just to see what it does. It's moving it. Well, this thing was way open. So you can see it moving. Yeah, it moves rapidly if we tighten it right up. So we got some movement there. It's in roughly the same place too. They're all tuning up roughly the same place. Okay, last one. Now this one, the primary side had half the resistance of all the others, suggesting a problem. Well, look at that. I will adjust the adjuster. The trimmer, really. This one was wide open. I'm tightening it. And there you can see the movement again. So we have a pretty good opportunity here to tune this guy up. There's some funny little greavies in here. There's a little bump right here. And see how there's a dark shadow here. Maybe that's just because of how long this line is. What's this thing right here? Okay, hard for you to see it. Let's see if I can just... Again, what the camera sees and what my eye sees is completely different. Okay? Both of us seeing nothing right now. There we are. So a little more brightness. Not too much. There. So you can see that this funny little weird thing happening here. This is probably the lower frequency, the actual frequency being visible, because remember the frequency is rising all the way across here. So that's probably what you're seeing over here is the actual input frequency. Very good. I think that's very good. What have we found out? We have found out that all four of those transformers want to tune in roughly the same frequency, including the one with the funny resistance. So this means I can adjust these, I can align all these. So if we can get the oscillator working, get the mixer working, looks like we do two amplifiers and then this is the mixer in here. No, that doesn't make sense. The mixing has to happen right out here because you have to have the IF frequency available. So the mixing has to happen right in the first tube. Must be the case. So I'm thinking of fill these up with tubes. Transformers are ready. We're ready here. I think I can make this radio work. I just need some tubes, some voltage, some luck, and according to the clock, some lunch. I need that too. Good so far.